Hello, Mr. Debussy here, and welcome to the January 2026 Unit 2 Physics AS paper, Waves and Electricity. I don't actually have the mark scheme for this, couldn't find it, but we'll have a go at the paper anyway. So the graph shows how current varies with potential difference for an electrical component. Which component is represented by this graph? This, my friends, is what we call a diode. And just give you a bit of a recap on how diodes work. For negative potential differences, so this is all negative potential difference, or for any potential difference below what we call the threshold, so this is the threshold voltage, and that's usually around 0.6 volts or around maybe 0.7 volts sometimes. So any voltage less than the threshold or any negative voltage shown by these two sections, the resistance will be infinitely high, a really high resistance, making the current will be equal to zero. There will be no current flowing through. So diodes, which have this symbol, only allow current to flow through in one direction. If you're wondering what direction, well, you see the diodes like an arrow. Okay, if the arrow matches the direction of conventional current, so conventional current is from positive to negative, right, from your positive to your negative terminal, then if that direction of the conventional current matches the direction of the arrow, it will allow the current to flow through. Don't get this confused with actual current. So if I have a circuit, let me give you an example. I always go in tangents, I can't help it, sorry. So if I draw a circuit here and have a diode, so actual current, always the big one's positive, right, big happy, and then small and negative. So actual current flows in this direction over here. And you can see the actual current is in the opposite direction to the diode. This will actually allow the current to flow through, because if actual current is flowing in this way, conventional current will be flowing in the opposite direction. So let me draw conventional current. Conventional current will be flowing in this direction here. And you can see that the conventional current is traveling in the same direction as the diode. So if conventional current travels in the same direction as the diode, or actual current travels in the opposite direction to the diode, it will allow the current to flow through. Otherwise, what will happen is what you see in this graph here. So for negative potential differences, when you switch the direction of the electron flow, the resistance is infinitely high and the current is zero. All right, so that's how you'd answer any explanation question 2. Here it says a phone is connected to a charger. The current in the charger is 5 milliamps. Okay, let's be careful. Milli means multiplied by 10 to the minus 3 or divided by 1,000, same thing. Which of the following gives the coulombs, gives the charge in coulombs entering the phone in 8 minutes? Now again, we're going to do the same thing here. 8 minutes meaning 8 times 60 seconds, because you always use seconds in all of the equations. So the equation for a charge is current times time. Really simple question. So 5 times 10 to the minus 3 multiplied by the time, which is 8 times 60, and you can see what matches this is C. Alright, here it says an electron in the ground state absorbs a photon. Which of the following could not be the energy of the photon? For the electron to absorb the photon must have exactly the right amount of energy, which is the difference between the energy levels of the transition. So if it goes from n equals 1, if it transitions from n equals 1 to n equals 2, it will absorb a photon with 13.6, that's the energy it has at n equals 1, minus 3.4, that's the energy it has at n equals 2. And that gives you, let me pull out my calculator. What was it, 10.2? I could do this one in my head. Okay, so 10.2 electron volts. If the photon does not have 10.2 electron volts of energy, then the electron will not absorb it. It's impossible for the electron to absorb it. Okay? Even if it has something really close, like let's say it has 10.23 electron volts or 10.3 electron volts, it still will not absorb it. If it has something less, like 10.1999 electron volts, again, it will not absorb the photon, because the photon must have the exact energy, which is the difference between the energy levels. So 10.2 is possible. I could see 10.2 here. We could also transition from n equals 1 to n equals 3. So this transition over here is also possible. And for that to happen, you must absorb a photon with energy 13.6 minus 1.51. This one gives you, this one I need a calculator, 12.09 electrovolts. Wallah, I was so good at calculations, mental maths when I was younger, but I'm getting old. Sometimes I find myself doing like 12 times 7, which is so easy to do, but I don't know what's happening to me. Guys, I'm aging. So 13.6 minus 1.51, then you also have 13.6 minus 0.85. And this is when it transitions from the ground state to n equals 4. And for this to happen, it must absorb a photon with energy equal to 13.6 minus 0.85, which is 12.75. So it can absorb a photon with 12.75. I can see 12.75 over here. It could also absorb a photon with 12.09. So all of these are possible. So we could just do process elimination if we're lazy and say therefore A is correct. However, let's do this properly and let's see what the final transition is. And that is from n equals 1 to n equals 4. Or n equals 5 actually, this will be. And this will be when the difference in the energy levels will be 13.6 minus 0.54. That will be 13.06, I think. And that's not an option. So yeah, 100% 9.8 is not possible because 9.8 doesn't correspond to any difference in any energy levels. So yeah, it will not absorb a photon with 9.8 electron volts, but it can absorb any of these photons because they have the exact energy required for transitions. Alright, here it says a light-dependent resistor is connected in series. Now I'm going to take this as an opportunity to remind you guys how light-dependent resistors work. And basically, for a light-dependent resistor, it has electrons inside. I'm really oversimplifying here. But when light is incident, and we know light is photons, what happens is the electrons absorb the photons, and what happens? Oh, sorry, I kind of explained it wrong. There's atoms with fixed electrons, and there'll be atoms with delocalized electrons. So that's supposed to be a fixed electron. Let me just fix properly. That's supposed to be fixed electrons. So there'll be atoms with fixed electrons, and there'll be atoms with delocalized electrons. So it's kind of like almost like a semiconductor. It can conduct electricity because there are some delocalized electrons, but there's not that many. And what happens is when the photons are incident, okay, these fixed electrons, they will absorb the energy from the photon, and then what would happen is it would delocalize. So now the electron is free. So when the light intensity increases, there will be more photons. The number of conduction electrons will also increase, or the charge carrier density will increase now. There is more free electrons available because the fixed electrons, these fixed electrons, they will absorb the energy from the photon and they delocalize. Okay, now because there's a larger number of conduction electrons available, the current will also increase. And a larger current will mean there's a smaller resistance. So to summarize, as the light intensity increases, the resistance of the LDR will decrease. Okay, now let's read the question and see what we have to do. Okay, it says the internal resistance is negligible. The light intensity incident on the LDR increases. So again, when the light intensity increases, the resistance will decrease. So now we're going to have a smaller resistance. Which row of the table describes what happens to the reading on a voltmeter and ammeter? I've noticed that the LDR is not connected in series with any component. So right now, the LDR is going to take the full voltage. The voltage, the 12 volts, the EMF, is not shared with any component. The LDR will take the full EMF. Okay, if I had a component in series, it changes everything. Let's say I had a light bulb in series. Now they're both sharing the 12 volts. So for example, let's say they both had 6 volts each. And this is a hypothetical. If you increase the light intensity of the LDR, the resistance will decrease. And because there's a lower resistance, there will be less collisions. Less collisions with the LDR, so less energy transferred. And we know that voltage is the energy transferred anyway per unit charge. So therefore, this will have a smaller share of the voltage. Voltage and resistance go hand in hand in series circuits. Okay, now because this takes a smaller share of the voltage, if it used to have 6 volts, maybe now it only has 3 volts. Meaning that the component is in series to will have a larger share of the voltage. So this will now have 9 volts. Notice they still add up to 12 because the EMF in series is split. But that's not relevant here. In this sort of question, when light intensity increases, the reading on the voltmeter will stay 12 volts because it's not sharing the voltage with anything else. So the voltmeter reading will stay the same. As for the current reading on the ammeter, well, we know current, and we can say this is the total current because notice the current flowing here is yet to split. If there were components, like there was another component in parallel, then the current will split into different values. But right now, this is the total current. So we could say that the total current is equal to the total voltage, which is the EMF, over the total resistance. Now, the total voltage is just always 12 volts. The EMF is just always 12. That's a constant. But the total resistance will decrease because as the light intensity increases, remember, the resistance will decrease. So you're going to be dividing by a smaller number, so the total current will be larger. Because if the EMF is constant, we could say that the current is inversely proportional to the resistance. So smaller resistance will give you a larger current. So the current ammeter reading will increase. So the answer will be B. I feel like I'll be waffling too much. I feel sorry for whoever's watching, to be honest. I can't help it. So light from two sources, S1 and S2, is in phase. Okay, the light has a wavelength lambda and meets at point P as shown. The path difference is lambda over 4, a quarter of a wavelength. Which of the following gives the phase difference? Okay, so first of all, they leave in phase. So from S1, let me draw S1 and then S2. Okay, so they both leave in phase. So we're going to draw them leaving from the same starting point. So this is the first one. Copy and paste it here. And this is the second one. You could see that they left in phase. They left at the same phase. All right. Now, one of them travels an extra quarter of a wavelength. Okay, so let me do that. Let me draw a quarter of a wavelength extra. So let's say S2, I think S2 traveled a extra quarter of a wavelength. This is a quarter of a wavelength because look, if you have, this is one wave, this is half, and then this will be a quarter. So I just draw a quarter of a wave here. So this traveled an extra quarter. So now what happens is this point here meets with this point here. And when they meet, okay, at point P, when they meet, okay, this is point P. They're going to meet at point P over here. These 2 points will meet at point P. At point P, what is the phase difference? Well, to answer this question, what we're going to do is we're going to draw just one wave. And we're going to realize that one of the first wave, S1, reaches point P when it's at this point. Okay, you can see it when it's at this point over here, it's reached point P. As for wave S2, it reaches at this point over here. Again, you can see it reaches at this point over there. And now you just ask yourself, what's the phase difference? Now you could either, if you compare these 2 points here, you could say that the phase difference is 270 degrees or 3 pi over 2. Or you could notice that actually this point is the same as this point over here. Because, every 360 degrees you're back to where you started. So always in a wave, the point 360 degrees could also be considered the point 0 degrees. Because it's just a moment of perspective. Did the wave start or did it stop? It doesn't matter because it starts and stops at the same point. So if we compare these two here instead now, these 2 points, you can see the phase difference is now just pi over 2 or 90 degrees. So the answer would be either 3 pi over 2 or pi over 2. They are both correct. Okay, don't get this confused. They are both correct. There's no 3 pi over 2, but there is pi over 2, so C will be the correct answer. Okay. A student investigated stationary waves on a string using the apparatus shown. The vibrating length of the string has a mass of 0.005 kilograms and a length of 2.5 meters. Which of the following gives the speed of a transverse wave on a string? Now, every time you see speed of a transverse wave on a string, there's only one equation you could ever use, and that is the speed of a transverse wave on a string is square root the tension over the mass per unit length. Now, the tension is actually 20 newtons. Fun fact, if there is no force, if there's no actual tension pushing the string, then the tension just becomes the weight of the string. because it's the weight of the string that will, you know, push it down, and that's just equal to mg. But because there is an actual tension, we no longer say the tension is mg, rather we just keep it over here. Now technically speaking, it should be 20 plus mg, but mg is probably really small. The mass of the string is probably really, really small, so we're just gonna keep it as 20. All right, so the tension is 20, and divided by the mass per unit length. Well, mass per unit length, as the name suggests, is the mass per length, right? Mass over length, and this will be 0.005 over 2.5. Okay, that's the mass over length. So let's substitute that in. So 0.005 over 2.5. And what you could do now is you could take this to the top. Simple maths rule. If you ever have A over B over C like this, or B over C is in brackets, which was the case here, then you just take the C on top. And then the correct answer would be 20 times by 2.5 over 0.005, which is B. Alright, question 7. Always second down myself when there's no mark scheme. Okay, which of the following graphs represents the relationship between the frequency and the wavelength of photons? Well, photons are light. Okay, light consists of photons. Or, you know, not just light, all parts of the electromagnetic spectrum consist of photons. And all photons travel at the speed of light, because they're electromagnetic waves. So we could say that the speed of any wave is frequency times the wavelength. But the speed of a photon would be the speed of light, and that's a constant. So the speed of light is equal to frequency times wavelength. Now, to know the relationship between frequency and wavelength, we could just make either one the subject. So for example, frequency is the speed of light over the wavelength. And because c is a constant, we can now say that frequency is inversely proportional to the wavelength, meaning when one increases, the other decreases. The only graph that shows when one value increases, the other value increases will be D, because A shows that when one increases, the other increases, they're proportional. This one here shows that when frequency increases, so does wavelength, but frequency increases at a decreasing rate, kind of like the current voltage graph for a filament lamp. It will look the same. As for D, well, D is the correct answer, because you can see that when the frequency is really high, you can see as the frequency is getting higher and higher, here's the frequency, the wavelength gets smaller and smaller and smaller, and vice versa. When the wavelength gets higher and higher, the frequency gets smaller and smaller. So this is how the inversely proportional graph looks like. I'm sure you've seen it before. For example, you know that for constant temperature, pressure is inversely proportional to volume, and this is how the pressure volume graph looks like. So any two variables that are inversely proportional will just look like this over here. Really important you memorize this shape. Okay, as for question 8, the circuit diagram shows a potential difference V applied across the ends of a uniform wire of length L. Which of the following gives the potential difference across length X? Well, first of all, you have an EMF of V, and this is going to be distributed to this wire. So if you have the full length L, then the potential difference across the full thing, so if I maybe connect a voltmeter like this, okay, the voltmeter will read V, the EMF, because there's nothing else to give the voltage to other than this piece of wire. Now what you should know is that the length of the wire, okay, the length of the wire L is proportional to the resistance. Because if you have a longer length of wire, then the electrons have to travel a larger distance. They're more likely to collide and transfer energy. So a longer wire will result in a larger resistance, common sense. So therefore, we could, because length is proportional to resistance, what that means is if the whole length has a voltage of V, if you had half of the length, for example L over 2, okay, that will have a voltage of V over 2. If you had a length of 2L, for example, then it would have a voltage of 2V. Obviously that's not possible in this particular question, but we know that length is proportional to resistance. So whatever happens to length, the same thing happens to resistance. So therefore we could say that if you have a length of X over L, then the voltage will be X over L of whatever the voltage was before. If X is L, if X for example is L, so you had the full length, then what you could do is L over L over times by V, and that just gives you V, because the L cancels out, and that obviously makes sense. So So therefore, it will just be x over L times V. Just B. I know the answer is B 100%, but I'm just so bad at explaining the maths part. So hopefully that made sense. Question 9, it says a ray of light is traveling through a material of refractive index 1.75. The ray is incident at the boundary with a material of refractive index 1.4 as shown. Which of the following expressions gives the condition for total internal reflection? Well, there's two conditions for total internal reflection. The first condition is it must travel from a more to a less dense medium, which is what's happening here. A more to a less dense medium. You can see the refractive index is 1.75 here and 1.4 here, so it's traveling from a more to a less dense medium. The second condition is the angle of incidence has to be greater than the critical angle. In this case, the angle of incidence is theta, so theta, which is the angle of incidence, has to be greater than the critical angle. And that's the condition that this question involves. You could see from the options given. Now, the critical angle could be worked out using the equation sine the critical angle is equal to the refractive index of your less dense medium over the refractive index of your more dense medium. The nice thing is if you ever get this confused and you do more over less by accident and then you try work out C, you're going to get a maths error. So if you ever get a maths error, it just means you had it switched around. So therefore we could say that the critical angle C is equal to sine inverse the less dense medium, which is 1.4, over the more dense medium, which is 1.75. And we know that theta has to be greater than this critical angle. So A will be the correct option. You can see theta is greater than this critical angle, sine inverse 1.4 over 1.75. Yeah, so far this is a decent paper, to be honest. When longitudinal waves pass through a material, compressions and rarefactions are formed. Which row of the table is correct? Well, in compressions, the pressure is maximum because the particles are close together, and in rarefactions, the pressure is minimum because the particles are far apart. So for example, if I draw like a slinky, you can see here the particles are close, we've got compression here, they're far away, it's a refraction. So we're looking for minimum. The pressure is minimum at refraction. As for the displacement is always zero. The displacement at a compression and refraction, I'm going to draw one here. Let me draw compression for you guys. But it's the same thing for refraction. So in a compression, you have a particle here, and then the particle on the left is really close to it, you could see, and the particle on the right is really close to it. So you could see that the particle on the right has a negative displacement, and the particle on the left has a positive displacement. This allowed for all three particles to be really close now, and that's a compression. But notice at the center of the compression, at the center of the compression, the displacement is zero. The particle is not displaced. The same thing is true for refraction. I'll draw refraction here. One more, so it makes sense. So in the refraction, what's happening now is the particle that used to be over here moves away. So it's now over here. Okay? And the particle that used to be over here is shifted to the left. So it's now it's over here. Okay, now you can see this is a refraction. Now you can see in the middle of the refraction, the center of the refraction, the displacement is zero. This particle has not been displaced in your center of your refraction. Whereas in the right hand side of the refraction, you have positive displacement, and the left hand side you have negative displacement, kind of the opposite to a compression. If you were to draw this as a displacement distance graph, for example, this blue one will be a refraction, because to the right hand side of the refraction you could see there's positive displacement, and the left hand side of your refraction you have negative displacement, whereas this will be a compression because of the opposite. You see in the right hand side you have negative displacement, and the left hand side you have positive displacement. Hopefully I didn't confuse you. Alright, let's do question 11.